So, morning. I'm Song Lee from NU, and I'm going to talk about the fundamental metallicity relationship, which is the relationship among three different key parameters of galaxies, which are the sublimation rate, stellar mass, and metallicity. So, when we talk about the metallicity, we have to talk about this most famous paper by Tremonti in 2004. They use the local single fiber spectra of Sloan to find that there is a very tight relation between the gas-phase metallicity and the stellar mass. So the scatter is only about 0.1 dex. And further works find that this relation evolves through cosmic time. So the normalization is larger when it is earlier, but the slope does not change. So even though this relationship is so tight, but astronomers just don't get satisfied. So sorry, just don't get satisfied. Yeah, and they want more. They want to further reduce the scatter. So they find whether there is another dependency of other parameters. For example, the sublimation rate, because we also don't know that there is a tight relationship between the sublimation rate and stellar mass in local universe. That is called the star-forming sequence. So in 2010, Manussi found this tight relationship. So they find that there is a tight surface in a 3D space constructed by the sublimation rate, stellar mass, and metallicity. And the scatter is only about 0.05 dex, so that is very tight. And the most intriguing thing is that they find this relation, this surface does not change, doesn't evolve through cosmic time. So the evolution of the stellar mass versus metallicity relationship is just the evolution of the star formation rate. So it just spans different regions of the same surface, but the surface itself does not change. So it is why it is called the fundamental, because it is not evolved. So now two questions arise. The first one is that is there a real dependency on the star formation rate? And the next one is it is really a fundamental relation. So does it really not evolve through cosmic time? So we'll find that these two questions are very controversial because, for example, if we change the metallicity indicator, then the normalization could be changed and the dependency of sublimation rate could be disappeared. And also we have the aperture bias. By aperture bias, I mean, so all the formal works are based on the single fiber spectra, which is the Sloan focused on the central 3 arcsecond. So if the galaxies are in a different distance, then it will span different physical regions in the same galaxy. So in this paper, they choose one elliptic radius. This is a fixed physical extent of a galaxy, and they find that the dependency of the sublimation rate disappears. So we have too many questions, but I just leave them here, and I want to talk about another topic. All the former works about the metallicity relationship are all based on the star-forming galaxies because the metallicity indicators are developed on the star-forming galaxies. But we have a lot of galaxies like the AGNs or shocks. We don't want to eliminate them. We want to add them in our sample. So we have some way to dissect the contribution of AGNs and star-forming regions. For example, that can be as easy as just evenly scale the relative fraction of AGN and star-forming regions on the BPT diagram from the lowest point to the highest point. And it can be complicated as invoking the model grids on the BPT diagram. But those methods are based on very strong assumptions, and they only use like 4 emission lines that can reveal very restricted information. So we want to solve all these problems. We want to make use all of the emission lines, and we want to get rid of all these strong assumptions. So before I get into my method, I want to talk about the models we use. The first one is the H2 region model, which means that the photons are radiated by the OB stars. Imagine the gas metal scaling is adopting the galactic concordance, which is a new scaling relation. That is based on 29 nearby B stars, rather than just one star, that is solar. The advantage of use this as a fusion point is that it is an average value of 29 stars, rather than just one star, so it is more representative. And because B stars formed recently, so it can reveal the recent gas properties of where they're born. And they use a nonlinear scaling function, which is more realistic. Because the gas properties are based on the galactic importance, we want to match the metallicity of the gas and the stars. So we want they're self-consistent, not a discrepancy of that. So we want the stars also use the galactic importance. So in our work, we adopt the Stromlo evolution tracks, which is adopting the galactic importance. The setup of the sublimation history is listed here, and you can have a glance of that. I don't want to talk about that. I just want to show that here is the example of the radiation fields of our evolution tracks and all other evolution tracks, which is based on the solar scaling relation. And you find that we have very harder ionizing photons, the blue one, comparing all others. Those harder ionizing photons moves the grids, the output grids from mappings on the diagram toward the right. So that means we have, for example, these red ones are the Stromlo evolution tracks, and the orange one are the original Padova track, I randomly find one. And you see that it moves toward right to have larger H2, the nitrogen 2 emission line and larger sulfur 2 emission line, and which matches the observation data better. And that doesn't matter. Oh yeah. And the Neuland region model, we choose the OXAF data code, and they have 3 different parameters, and we fix 2 of them, and just release this energy peak of accretion disk as the free parameter. So we want to use our method on FU data based on the Bayesian method. So the workflow is like this. So we have the stellar radiation spectra, and we put it into mappings, and we output the grids, which have 3 intrinsic parameters: the pressure, the metallicity, and the ionizing parameter. And we also do the same thing for the AGN spectra. And we combine these 2 grids together and evoking another parameter, which is the fraction of H2 regions on the H beta emission line. So right now we have 8 free parameters, but that is a huge amount of parameters. So we want to reduce that. We have these several preliminary, we predetermine the energy peak of accretion disk for one galaxy and the ionizing parameter of H2 regions and fix them for one galaxy. And because for each spaxel, all the gases are from the same region, so we think the pressure of H2 regions and Neuland regions are the same, and the metallicity of them are the same. So right now we only have 4 parameters: the pressure, the metallicity, the ionizing parameter of Neuland region, and the H2 region fraction. So by the grids, we mean that we have a bunch of free parameters, intrinsic parameters, and we combine all of them. For each line is a combination of some of them, and we have a huge list of emission line fluxes. And the basic method is like this. Just imagine, for example, if I find a picture of some of you on the floor, and I pick it up, and I try to find who it belongs to, so I just compare this picture to all of you one by one and try to find a very similar one, the most similar one. And I think, okay, this one belongs to you. But I can have some other information. For example, if I find it on the women's toilet, no, sorry. It's like weird. If I find it on the men's toilet, and even if I find it is very similar to a woman, I don't think it belongs to you, right? Because I think it belongs to a man. So this is called the prior, but I don't have to do that for all our models. The computer do that for me. So we want to implement the Bayesian method on all the FU data, and we have 3 advantages. The first one is that we can add the AGN contribution of our samples, and we can investigate their properties rather than just suburban galaxies. And we use FU data because, firstly, we investigate the spectral spaxel by spaxel, so that can reduce the mixing light from all other contents. And we can choose a single physical aperture to remove the aperture bias. And the final thing is that we can take use of all of the emission lines rather than just 2 or 4 emission lines. So, okay, I have 1 minute. I will show you an example of the one galaxy. So here is one manga galaxy, and you see that there is a separate one AGN in the center. And we put it into Nebula Bay, the Bayesian method, and we can output 4 different estimated maps. The first one is the abundance, the oxygen abundance. And you see that here is a clear negative gradient from the center to the outside, which makes sense because we know that most of the AGNs are metal rich. And the second one, One is a pressure map. And the interesting thing is that for most of the star forming regions, it hits the lower limits of our model. So previous work also found these effects. So they found there is a discrepancy of the lower limits of the models, simulated one, and the observational data, and there is no solution right now. And the third parameter is the L-Nelson parameter of Nebula region. We find there is a large enhancement in the center because it's a separate galaxy, so the L-Nelson parameter is very large. And okay, I will. And the final one, this is very consists of our anticipation. So we find that the H2 fraction in the center is low because it is a separate one. So that makes sense. And our next step is implement the nebula base on all the mega galaxies. And we try to calculate the oxygen abundance and star formation rate based on the H2 fraction. And then we'll plot the fundamental magnetic relationship in mega galaxies with all kind of galaxies. Okay, that's all. Thank you very much.